think a new age looks like. Reenactment.
Why do you like princess movies?
Why do you like basketball?
Because that's a guy thing to like.
You think I'm not male?
I just find most of the male movies are
Well, it
not.
depends on what movie, because Rapunzel's or
There's
Tangled.
really no good, like,
Tangled's good.
male movies, I guess.
Yeah, that's what I'm saying. Like, the male movies are like not appropriate most of the time.
They're all either gender neutral or.
It's in the frog. Well, you can get,
Well,
they're all like Tarzan.
you got the triple act, which is pretty good. It's like no, like Xander Cage. Xander Cage. It's like the stunt guy. He basically beats up Russian spies and like drives cars really fast.
So this stuff, here's what I want you guys to write down.
I know.
It's not in your notes. I actually put it in the notes for next year.
It's Vin Diesel.
I want you to put this in the section where it says salts being compared produce the same number of ions. And I want you to put this in the one below it where it says the salts being compared produce different number of ions. So I want you to put this in for 1 and this in for 2. Alright. Then I want to kind of talk about this. So, yesterday we talked about KSP and its relationship to solubility. How KSP can only have one constant at a given temperature, but the solubilities could be different depending upon the conditions that you have. And what this section is talking about is this idea of relative solubility. You guys know what the word relative means, correct? When I say relative solubility, that means I'm comparing the solubilities to each other. They're relative to each other. Sorry, it's okay. I kind of like that. So, what this is saying is if all of your salts have the same number of ions, I can look at the KSP values and I can know which one's going to be more soluble. So, just for a little bit of practice from yesterday, the Griffin twins find the solubility of this. Grant and Ryland find the solubility of this. And you two find the solubility of this. It shouldn't take more than a minute, probably.
Wait, the second one? That's easy.
They're all the same process.
They are.
Are you finding the quick ratio or quick way to solve for solubility when you have a ion that breaks up into 1-to-1 ratios? Just take the square root of KSP and voila, you've got the solubility. And I don't remember who I said AGI was doing that. What'd you guys get?
1.22 times 10 to the negative
Both confirm that? So then that would be concentration, correct? Ryland or Greer, the next one.
2.277.
And 182.
0.0078.
All right. Now, if I were to figure out or ask which one of these salts is more soluble, you guys would all say which one's the most soluble. What does soluble mean? Okay, so which one has the most dissolved? From a solubility standpoint, CaSO4 is the most soluble, followed by this guy is your most soluble. Now, if they have the same number of ions, you do not need to find S to figure this out. You can just look at the KSP values. Which one has the highest KSP value? The most soluble one. Which one has the lowest KSP value? The least soluble one. So if they have the same number of ions that they give off, you can just quickly look at the KSP values and find relative solubility. If they do not have the same number of ions, you cannot just look at the KSP values. You must find their solubilities. Okay? So if I go down here, this is a 1-to-1 ratio, so you just take the square root of KSP. This one's a 1-to-2 ratio, so this is S squared. Anybody know what the 1-to-2 ratio one is?
4S.
4S to the third. And a 2-to-3 ratio, do you remember that?
108, yeah.
What'd you say? Okay, so Sam Griffin, why don't you guys, Griffin's brothers, why don't you guys do the first one? Ryland and Grant do the second one, and two ladies do the third. Assuming you guys got it?
9.22 times 10 to the negative
Check. Ryland?
3.42 times 10 to the negative 17. Is that what you want?
Yeah.
Emily? So KSP divided by 108 to the 5th root.
You do 5 and 5.
You can do it to the 1/5 too.
Yeah.
Power, right?
Yeah.
What you get?
1.002.
All right. From the solubility numbers, which one's the most soluble?
Pt2.
Okay. Then our AGS2 is next. And our CUS is the least soluble. Would you have been able to figure that out looking at the KSP values? CUS actually has the highest KSP value, but it's the least soluble. Typically, the more ions they are, so the more ions you have, the more soluble it is. They might know why that would be. Just wondering if you could make that connection.
Weaker bonds.
No.
They're actually probably slightly stronger bonds, but the bigger kicker here is they have a stronger charge.
Oh, okay.
And so they're attracted to the polarity of water a lot more. And so yes, even though these bonds might be a little stronger, because they're more polar, they're going to be attracted to water even more. And that's why that's probably going to dissolve more than the other. Okay? So in the end here, the thing that you must know is if they're 1-to-1 ratio, or if they have the same ratio of ions, you can just look at the KSP values to figure out which one will dissolve more. If they are not, then you actually have to solve for the solubility, but as you guys have seen, it's not overly difficult. Okay? So, what happens if we have a common ion? Because we said the solubility can change if a common ion is in solution. This is kind of leading us slowly towards tomorrow's lesson, which is going to be the most difficult one of the chapter. Okay, so it says consider the solubility of this guy, but we've already got 0.1 molar solution of AgNO3. So we are taking and trying to dissolve this in this. Okay, what's the common ion? Right? So let's just break this guy down into our equation. We got Ag, CrO4. Yeah? KSP expression. Don't put my what in.
Isn't it 0 for sigma?
Yep. Catch. Okay, for all of these solubility things, safe bet to just write the equation first, then the KSP expression. Any ideas what you might do now?
Solve for solubility times
So it's not going to be just doing what we did yesterday where we're just going to plug in, although technically when we do S and all that, it's a modified version of an ice table. But because we have an initial concentration of one of our ions, we should probably just do the safe route and make an ice table. Okay, that's a solid. I have a common ion. We said it was what? So I should have an initial concentration of that. What is the initial concentration of that? 0.1. Okay, now if this were Ag2, it would be what?
0.1 times
So be careful. The ion ratio is important. If we do know it completely dissociates, but if it's not a 1-to-1 ratio, we have to take that into consideration as well. So 0.1 and 0. Now I'll just go back to use, well, yeah. You want me to put X, just use X here, or would you prefer S? Doesn't matter. in. Okay. Now, is our KSP big, small? What is it? It's really small. So what's the rule if we got a small equilibrium constant? Okay, we can assume that this is so small in comparison to this, correct? So we can just do what? Remove it. Make it a little bit easier on us. So what we have is x, so the KSP, divided by 0.1 squared.
There's 0.0.
Yeah, probably. That will give us okay, now that is x. Now we could go back and do the 5% test, but look at how small that x is. Everybody see it? Okay, now it wanted the solubility of this, but notice the relationship between x and this. It's what? 1 to 1. So if I know the solubility of this, I also know the solubility of this. So this is our answer. That's how much will dissolve when I have a common ion of 0.1. Now we could have done it, well, let's see. Yeah, let's just do it quickly if it wasn't. Just to kind of help connecting here. Thank you. So if we didn't have AgNO3, what would we do?
If you didn't add.
If we didn't have the AgNO3, we just said, what is the solubility of Ag2CO4 when we plop it in water?
It's 2 to 1.
Yep. So S would be, someone do this for me, I don't know what it is off the top of my head. Now, what would you expect this number to be, bigger or smaller? You would expect it to be bigger based on the Le Chatelier's principle. A common ion is going to shift the equilibrium which direction? That way, right? So when I have the common ion in there, this is going to dissolve less. When I don't have the common ion in there, it should dissolve more. And what was the number?
1.377.
Okay? Just a quick review from what we've done in the past couple chapters, so we don't forget some of that. Okay? Now, they might ask you, what is the concentrations of these two ions at equilibrium? Well, if we know our X, just plug into this to find your equilibrium concentration. Does that make sense? If I take this and plug it in, is that going to change 0.1 at all? So you would really say the concentration of this is just 0.1, and the concentration of this is 9 times 10 to the negative 10. Okay, and I think, I'm thinking they were maybe asking you that for this one, but it doesn't appear so. Why don't you guys do this one? Same idea, common ion. Let you guys do this one on your own. How we doing? What you got?
That had 0.64.
Did you not have the right KSP? So this number divided by 0.025
Yeah.
squared?
Yeah.
Did you just do that?
That's what I did.
Oh, I mean, yeah. But we're gonna get rid of the 2x.
Yeah.
But I just,
Yep.
Yeah, even that ain't
Did I mess something up? I mean, I got rid of the 2x here because
I got it this time.
it's so small. Okay, and since 1-to-1 ratio here, that's our solubility of CaF2. Now, we couldn't find the solubility without the common ion. You would expect it to be more soluble without the common ion. Now, last thing that I do want to cover quickly, but are there any questions before I move on? I see some people still typing into your calculators. Did I, anything I can do to answer a question for you? Nate, did you get that? Okay.
Yeah.
pH and solubility. In fact, this was kind of cool because I experimented with this very concept when I was working in the lab a couple summers ago, and I was trying to increase, or I was trying to purify something. I was trying to mess with solubility by changing the pH, and basically, essentially doing, kind of a common ion idea, but more or less just really a reaction. But let me kind of point out how pH can possibly affect solubility. So let's say I want to add this to a particular solution. Let's say I add it to a solution that has a high pH. What does a high pH tell us we have a lot of?
No, OH.
OH. High pH means we have a good amount of OH minus in solution, correct? Alright? So if you got a good amount of OH minus already in solution and you add this, what's going to happen? I add this salt. I add this salt to a solution that has a high pH. What's going to happen to the solubility of that salt? Is it not going to be affected? Is the solubility of that salt going to go down or go up versus what it would do if it were a neutral pH?
I'm assuming go down because you said you're trying to purify stuff with changing pH.
Well, that doesn't mean I was doing it this way.
I'm assuming you did it this way. Yeah.
First off, I have a lot of this, right? Isn't that a common ion? So if I already have a bunch of this, how is that going to shift the equilibrium of this solubility? Are we struggling with this concept? Yes? You don't remember Le Chatelier's principle?
Stressors, parts.
Okay? We added, we have a bunch of product. Is it going to produce more product? No. It's going to shift the equilibrium to the left, which means the solubility decreases. We just did two problems where we had a common ion that decreased the solubility. I just gave an example. I'm about to show you what happens if you have a low pH. If you have a low pH, what does that mean you have a lot of? Okay? If I don't have a common ion anymore, but I do have something that will react. What is that H plus going to react with? The OH minus, right? What does removing a product do to the equilibrium stress or shift? It's going to shift it right, which means this is going to what? Okay, yeah, so it'll dissolve more, is what you're saying.
Yeah.
Yes. When I say the solubility increases, I'm meaning that it is going to dissolve more, because as it dissolves, OH will react with H plus, removing the OH, allowing it to dissolve even more. Does that make sense? Okay, this situation. All right, let's say I have a low pH. Low pH means H plus. The question you must ask yourself, if there isn't a common ion, is there something in this salt problem that the H plus will definitely react with? PO43 minus. This is actually not a strong base, but it's one of the stronger weak bases because of that really strong negative charge. So, this will react with this, causing the solubility to what? Okay? Let's say we have a high pH or a low pH, but we try to dissolve AgCl. Just quickly, last one. Okay? This is going to break down into Ag plus and Cl minus. What will be the effect of the solubility in this situation? Solubility won't change. Why? Because is this going to react with H plus? Because if it did, it would be producing a strong acid, which is that you're producing something that will never be produced. It will always be dissolved. So, if this won't react with it, then the solubility would be the same had I had it just in a regular neutral situation. Now, if this were in high pH, it's possible. Okay? So you have to identify, is there a common ion, or is there some ion that will react readily with either H plus or OH minus, and figure out from Le Chatelier's principle which way it would shift. You're done. Come on in, guys.
Woohoo!